Hey, Algebra 2 honor students, this is going to be Unit 8, Day 4, and today we are getting a little bit of practice with some of the new theorems that we've learned about how to solve higher order polynomials. So we're going to see some more Descartes' rule of signs today and some rational root theorem, and we're thinking about some of the other theorems that we've learned, like root location theorem and upper bounds and lower bounds, and kind of putting all of that together to find all the roots of this cubic polynomial here. But one thing that we're going to see that's really the only new piece that we're adding on today is I'm going to organize the synthetic division in a different format than we've seen up until this point. And it's going to be in a chart. And although the chart takes a little while to get used to, I think you'll come to appreciate it as a way to organize your information, especially if it gets to a point where you're testing many, many roots. So let's go ahead and get started on this one. And first and foremost, we know that we're going to get 3 roots in the end because we have a cubic polynomial. So the first thing we might consider doing is maybe making a chart for the different possibilities for the positive, negative, and complex roots using Descartes' rule of signs. So in f of x, we would have positive, negative, positive, negative. Those are the signs for f of x. Okay. So what we can see is when I write down those signs, plus, minus, there are actually 3 sign changes in f of x, which is a little different than probably what we're used to seeing. But what that means about f of negative x is that it probably should come out to be 0. Because if we have 3 positive roots, there's only 3 roots total. So there really shouldn't be any negative roots then. But let's go ahead and see what happens when I look at the sign changes in f of negative x, which is changing the odd exponent signs. So it's going to change to negative for x cubed, but x squared stays. X, the first stays negative or becomes negative. The constant stays negative. So as we predicted, there are no sign changes in f of negative x. So when I go to make my chart for positive, negative, and complex possibilities, the first row says 3, 0, 0. At a max, you'll have 3 positive roots, no negatives at all, and then no complex roots. And the reason why we know it's no complex right away is because we have to equal 3 roots total for a cubic. All right, so then coming over here to say, well, what's the other possibility? The roots could turn out to be 1, 0, 2. So remember, if you can decrease a column by 2, because complex roots come in conjugate pairs, the other possible case that we consider here is that we'd have 1 positive, no negatives, and then 2 complex. Those are the only 2 cases that are possible given Descartes' rule of signs. So now we're going to move on to the rational root theorem. And the rational root theorem says take the factors of the last coefficient, which is the factor of 12. So that's going to be plus or minus the following possibilities. It could be 1 and 12, 2 and 6, or 3 and 4. So I'll list those in order. And then you're going to divide them by the factors of the lead coefficient, which is a 1. And we like when there's a 1 out there because then essentially you just get that list of numbers that are on the top. So you get plus or minus 1, 2, 3, 4, 6, and 12. We have a potential of testing 12 roots before we find one. Most likely we'll find one before we get to the 12th test, but there's 6 in this list and it's plus or minus any of those. Now we'll definitely not have to test 12 possibilities because even though I wrote plus or minus out front, we know that according to Descartes' rule of signs, there's not a chance of getting a negative root. So if I'm being smart about the process, I really shouldn't test negatives at all. Let's move on to synthetic division, which is going to look a little different today. The process is still very much the same. But let me show you what the new chart looks like. So you're going to create a column in your chart on the left called x. And in your x column, that's going to be a list of the roots that you're testing. So drop a vertical line there, a decent length down. And underneath x, you're going to put 0. Because what we're going to do is we're going to always test 0 first as a root. And by testing 0, we've done this once in class. What happens is you get just the coefficients of the polynomial up here. So you would get 1, negative 3, 4, and then the last coefficient, which is negative 12, we know that that's the remainder. So we're going to separate the remainders in another column on the right. And I'm going to call that column on the right f of x. Because we know the remainder in synthetic division goes with the y value given this x value that was tested over here. So what we're going to do is I'm going to kind of block off that whole row and say these are the coefficients that I'm testing and using synthetic division. But every root that I go to test over here, I know that the answer for the remainder is the y value on the function. The only thing that's different in this process is you're not going to write down that in-between line. You'll see what I mean when we start testing here. But usually we would, bring down the 1, and then we would multiply by the root and write that number down. But you're just going to sort of save that number in your head and add it to the next column so that you can figure out what's left. So let's just start the process and see what it looks like. I'm only testing positives from this list because of what Descartes told me. I'll start with positive 1. Why not? All right, I'm going to bring down the 1. And then this is what we're going to do. We're going to multiply by the root that we're testing. Same idea as what we've done leading up to this point. So 1 times 1 is 1. But usually we would write that down. I'm just going to take that 1 and add it to -3 to get -2. Multiply by the root. So -2 times 1 is -2. And then without writing that down, just add that number to 4. So it's going to be +2. Finally, 2 times 1 is 2. And 2 plus -12 is -10. So in conclusion, 1 is not a root. But that was what our first look at using this new synthetic division chart looks like. All right, let's try 2. Maybe 2 will work. So I'm going to bring down the 1. 1 times 2 is 2. 2 plus -3 is -1. -1 times 2 is -2. -2 plus 4, +2. Finally, 2 times 2 is 4. 4 plus the -12 is -8. Not a root. Move on to the next one on the list. Hopefully you're getting the idea of what's going on in the chart though, right? So let's test 3 because that's in my list. Bring down the 1. 1 times 3 is 3. 3 plus -3 is 0. 0 times 3 is 0. And then 0 plus 4 is 4. Finally, 4 times 3 is 12. And 12 plus -12 is, in fact, 0. So even though I think this chart format may take a little time to get used to, the nice thing about it is I don't have to write down those coefficients every time I wanted to test a root. Whereas everything up until this point, we would have just written those coefficients again and then done another test. So it's a little bit more math in your head, but really nothing you can't handle. So let's go ahead and take those remaining coefficients, which this is the coefficient of x squared. There is a 0 as the coefficient of x, and then we get a +4 at the end. So we actually get this quadratic that's left over. And because we don't have that middle x term, we can solve this pretty easily by subtracting 4 to the other side. And then square root, square root. So we get that the other roots are plus or minus 2i, right? When I take the square root of -4. So in total, my roots are, if I were to list them, 3. And then you can list the plus or minus 2i together for a total of 3 roots. But one thing I really want you to check back in on is, hey, those plus or minus 2i, it was this case right here that we got 1 positive root and then 2 complex roots, according to what Descartes' rule of signs told us. So when you check your roots in the end, you want to make sure they hold true for the other conditions that we've talked about, like Descartes' rule of signs and rational root theorem. Now, we didn't see any upper bounds or lower bounds by doing this process. We also didn't see any sign changes, which would indicate that root location theorem. But I promise as we do more practice with these, we're going to start noticing those things and hopefully helping us along the way to find all of the roots really efficiently. So that's it for today's lesson. It's a really short one just to kind of get us used to the new chart. Next time I see you in class, we'll do more chart practice and we'll go from there. Have a great day.